Okay, so this is just a short um, explanation as to why fitting data is a big deal. So, if you remember the stuff that we've been talking about, we'll say in chapter 3 and chapter 4, specifically dealing with, 1, 2, and 3 dimensional motion, but with constant acceleration. For example, kinematic equations. We know that we get a series of equations that can describe motion. For example, one looks like this, one looks like this, and there's a third one that we derived, which was time independent, which looks like this. Now, now these things right here are the results of theory. Okay. Now, remember the purpose here in the sciences, or at least in physics, is to model what we see. Okay. So you make some sort of observation, and by observation I mean that you measure stuff. Okay. And then you have, your theory. And the big question is, does your observation support your theory, right? So, just as an example of how fitting data falls into all this stuff, these are just mathematical equations. And not only that, they look a lot like equations that we've dealt with before over and over in, say, algebra. For example, the first equation here, your variables typically are v and rt, right? But if you look at v is equal to, we'll say, I'm going to rewrite this a little bit differently, a times t plus v naught. This looks a whole lot like y is equal to mx plus b, the equation for a line. And in fact, if you remember way back in chapter 3, one of the things we did was to interpret graphically what things like velocity and acceleration are. And in this case, if you were to, for example, make a plot, we'll say of velocity on the y-axis and time on the x-axis. Now, this would be, the y-axis, and this right here, typically, like I said, conventionally is the x-axis. If you were to plot it, and you end up with we'll say a straight line like that, then comparing the above equation to the below equation, the slope of this line is the acceleration. The y-intercept b would be what your initial velocity is. In this case, it would be 0. Okay, so the goal here is to make your observation and then plot the data points from your observation, typically as a scatter plot or something like that. And then what you do is you take one of these equations, these equational forms that we're so familiar with, like the equation for a line, or we'll say even the quadratic equation, which looks something like this. Um, ax squared plus bx plus c is equal to 0. Okay. So what you do is you plot these things, and you adjust the parameters, the things that can change, that change the shape of your curve, A, B, and C, or in this case, M and B, okay? So that you get as close to a fit, that is the line that you get when you plot this, on top of the line that you get whenever you take and you fit your data. They get as close as they possibly can to each other. Now, sometimes close is not good enough. Sometimes you want to be as dead on as you possibly can. And, that may or may not happen. So, as an example, just to show you shapes of curves and stuff, Right here is a plot of position versus time for a cart rolling down an incline. Okay. Now, what I'd like to point out here is that if you were to plot, for example, x is equal to x naught plus 1/2 a times t squared plus v naught t. This right here looks a heck of a lot like ax squared plus bx plus c if you associate your initial position with c, 1/2 a with this, and b with your initial velocity. And in fact, when you take and you plot this, okay, when you plot this equation right here with y being equal to that, then it will lie directly on top of it. And the parameters that are required, a, b, and c, in order to produce that result, you can then use to find, for example, acceleration, initial position, or initial velocity. For example, if you line these things up, whatever the c parameter is from your fit is your initial position. Okay? Whatever the b parameter is from your fit is your initial velocity. And whatever the a parameter is from your fit, that's equal to 1/2 times a. So for example, if I were to plot this and I wanted to find out what the acceleration is, I would simply solve this right here for a. So this is what I get from taking a strictly mathematical form for an equation, something that looks like this, fitting it to this, and then taking the parameters, solving for what I'm actually looking for. This is the link between this right here is the theoretical idea, and this right here is the empirical result. Empirical, E-M-P-I-R-I-C-A-L, there we go. Empirical result from observation. Okay, and this is the link. This is the link between the two. So ultimately, unless you're a pure theoretician who has they don't have their toes in the water of experiment at all, and no theoreticians are like that, except for maybe string theorists, then at some point you have to test. And this is the test. You observe, and then you see how close your theory can model nature through fitting data. And that's it. Okay, so this is a short tutorial on how to use Excel to fit curves and things. Now I've got two examples here. I've got a data set that's linear, and I have a data set that is what we call quadratic. That is, it looks like a polynomial with the biggest variable to the second power. Now, one of the things I'd like to point out here is if you look at these two columns of data, the first one is t, the second one is x. Excel likes to have its columns ordered such that the first column would be on the x-axis and the second column would be on the y-axis. So this would be a position versus time graph, if you remember way back in chapter 3 when we talked about those. So if I click here and I hold the shift key down and then click the bottom value, that selects what I want to plot. Now, I'm going to go up to insert because what we're doing is we're inserting a plot into our spreadsheet here. So I want a scatter plot. That's what we want whenever we plot data, at least this type of data. And if I select scatter, this is what I have. Now let's move this over here and just resize it so it's a little bit more legible. So there's our plot. And as you can see, visually, it looks like a straight line. And it really is. Now let's not forget that this axis right here would be the x-axis, and this axis right here is the time axis. Okay? So in order to get a fit for this, what we want to do is to go up to the right-hand corner over here on our plot and click the chart elements part. Now you'll see trend line down here. We want to look at more options. Let's do that again because Excel has issues. And as you can see with our trendline options, we have a whole bunch of different equations that we can try to fit this to. Now, it's all a matter of picking the one that fits the best. For example, if I selected exponential, as you can see, an exponential plot doesn't fit this very well at all. If I were to go to logarithmic, no, I don't think so. Polynomial fits, and that's because a line is a special case of a polynomial. Power, yeah, you can make a power fitted in this case. A moving average, probably not. Now this looks like a line. I'm going to select the linear one right here, and I also want to display the equation on my chart. Now this right here is the equation. The reason why we want the equation is because, whoops, let me select this and move this over here. The reason why we want the equation here, come on, behave. Come on, man. There we go. Nope, it's not going to let me make it bigger. That's fine, whatever. Anyway, so remember, this is y is equal to mx plus b is what it's trying to fit. It's trying to fit the equation of a line to this, which means that what you're looking at here is the slope of this line. Now, y here would be this axis right here, which in reality, remember, is the position, is x. The x-axis here would actually be time, t. So what you're really looking at here with the slope would be the equivalent of a velocity. So you could pick this off, and that would tell you what the constant velocity is in this particular case. So remember, the goal here behind fitting stuff is to try to take your measurements, and then through an equational fit, match them up with your theory. Now, another example of this is this quadratic right here. So this is a quadratic plot. I've put it together to look a lot like, a free fall problem with an initial velocity of 0, basically. So let's select this data here. This is, we're just going to plot it to begin with. So let's go up to our insert. We're going to insert a scatter plot. So here's our scatter plot right here. Let's put this in here. We'll move our graph over here and resize it just like we did before. Like that. Okay, so now as you can see, this definitely has, sort of this exponential increase right here. If I go over here, I'll select trend line, and then I go to my options. Hopefully it'll show me the options that I want. No, we're going to have to do that again. Thank you, Microsoft. Anyway, here we go. So you got a bunch of options here. A line is definitely not the best fit for this. As you can see, it doesn't go through the majority of the points. There's definitely some sort of exponential logarithmic trend to it, or not logarithmic rather, but a polynomial trend to it. So if I go to exponential, oh no, exponential doesn't fit at all. Look at that. You see how bad it is? We'll try logarithmic. No, that's definitely not a logarithmic plot. Okay, let's try a polynomial. Look at that. There is your logarithmic plot. Now, so let's once again display our equation on the chart. And the equation that you're looking at right here is of quadratic form. So polynomial raised to the power of 2. Come on, man. Come on. Work with me here. Come on. There we go. Okay. So what you're looking at here would be, remember, on the y-axis is position, and on the x-axis here is time. So this would be x is equal to this times t squared plus this time times t minus this is a constant. Now, like I said, your initial velocity, at least the way I did this, was 0. So 10 to the minus 14th. Look at this. These are terms that you can disregard. Okay, so this is very much, a plot to a polynomial. So if you were to take this and then below it write something like, x is equal to 1/2 at squared plus v naught t, plus, x naught, then what you do is you one-for-one match stuff. Okay, you match stuff to what's sitting in front. And, for something like this, you could solve for the acceleration, which would be this term right here. This would be equal to 1/2 a. So you would just solve for a. You multiply this by 2, you get, 9.8. So again, just a quick little tutorial on how to use Excel to plot stuff and how to get data, or at least to get information from your best fit here.